Okay, now we are going the next level with the same question. What happened when you have lines that are not straight lines? So, what's happening here? This should not be shown here. I made a mistake. So I have a couple of videos. Maybe I should show. No, but let's do this. I will copy this and you open in your computer because it will be better than copying it here. No, let me copy. And what is the chat? I lost the chat. Take a look at the video. Okay. And if you have the option of doing a slow motion. So this is an experiment that I did in class some years ago. If I had time this time, I would like to do it again, but it's not so easy. I mean, take 1 second. It's a 1 second video. So, okay, let me show it. But just stop it. So what I did here, I projected in the classroom. You remember when we had classroom, no? In the old time in our life, we had something that we call classroom. What here? Oh my gosh! Stop. So I projected a big screen in the wall, and I make a clock here that counted milliseconds. Okay, with the computer, I make a little program that was showing the time in milliseconds. So this is 3.156 seconds since I dropped the ball. Okay. Then with the cell phone, I asked someone to record. Different people, I asked different people to record. And some cell phone, well, I don't have cell phone anymore, but my cell phone before it died, you have the option of like slow motion. Okay. And slow motion, what they do essentially is take more pictures in every second. So let's see something like this. This is nice. So I essentially take a ball, an object, and drop it. And we have the time and position. Okay? Now, something that I did wrong is that I didn't measure the distance very carefully. And in fact, so the initial point is not very clear. It's not very clear if it started in 0 or where. I should put the starting point like here. This will be 0. So the idea that this was 0 centimeter, this will be 10, this will be 20, 30. But in fact, it didn't work like that because the distance here was like 19 centimeters. Was not very. So next time I will put a tape, a real meter tape here, and I will be more careful to start from 0. So, well, in general, every time you do an experiment, you realize you learn how to do the experiment better next time. So if you want, when we see physically each other again, after the isolation, we can try to do this experiment again. We can do from the last floor and record. I don't know. There are many things that we can do. But the point is, this was an experiment that was easy to do during the class. Okay? And in YouTube, you have even an option like playback speed, and you can even go slower. So you can really go like very slow motion, and essentially I write what was the second, the millisecond that it crossed every line. Okay. Even that is not very clear because you don't know if you measure when you start or when you finish. The ball that I dropped had some size. So it should be the start of the ball, the end of the ball, the middle, something like that. But anyway, the point is that the exercise was, I mean, it's something that you can do at home. You put your cell phone, or you ask someone to take the cell phone. You put a tape, the one that they give you for free in IKEA, and you drop something in and you record with the camera, no? Is it?
We did this last year in physics. We did this experiment in our houses, in our homes.
Ah, good.
In
So you have that numbers.
Yes.
Great. Everybody got that number? That was a very good idea. We should use your numbers.
We calculated a gravitational acceleration.
Ah, good. So you did this class already. Wonderful. How you calculated?
With drop something. And
yeah.
Time and.
With a round object, we dropped from a certain height and timed it, and find an approximate value and find our error later.
Ah, good.
Yes.
Good. I would like to say, write that report. We should write that report. But you are still not telling me something. There is something still missing in your story. So, but let's go to this, and then you tell me. I'm very much. I like people in the physics department do very good things. So, okay, you are seeing my screen, no? Yes, no?
Yes.
Okay. So we can close this one and take this. Then full screen. Very good. So I with some art magic, I make this picture. This is not something with this, but this is what happened. So this is taken in constant time, and you see that essentially the drop is balling the drop. The ball is dropping with a particular shape. What is the shape? What is this shape? Is this a straight line?
No.
It is the reverse of exponential growth, I guess.
No, it's interesting. No, the exponential decay is something like this. We should see that the exponential decay, like the price, we can see it in the price of the human genome or something like that. Okay, well, good access. No, but this is not. Exponential decay is going down and down, but never getting to zero. This is going to zero. Exponential decay never reach zero. I mean, you did this experiment already. Why you ask me then? Why you don't know the answer? Well, I make 2 videos because I did it twice. But if I was more correct, I should do it at least 3 times. You know, there is a basic rule that if you make an experiment, you can make an error and you don't know what you make. And if you make it 2 times and they are different, you don't know what is the right one. If you make 3 times, then normally 2 are equal and 1 is different. And you know that the one that is different is the error. Okay? The more experiment you have, the better result you get in general, the more replicas, I mean. You make the same experiment again and again. I don't know how many times you did in physics.
We did 3 times, but also we fall the ball from 100 centimeters and 50 centimeters, and also 30 centimeters.
These are different experiments.
I can mail you my homework.
I made a table. I can show it.
Okay. I can
the table I did.
Okay. So you have 3 experiments and you have replicas. I see. Let me do something. Let me do something. I will stop sharing my screen so we can see your screen. Okay. Very good. So 150 and 25, and you have what is the time? Time total, and then you have the average. Okay, this is fine. Yeah, and how you measure the time?
With chronometer.
With a chronometer. Okay. Good. I am using the camera as chronometer, assuming that the camera is taking a picture every and a fixed interval. But we need a way to calibrate. Yeah, good point. Then, but okay, so you essentially have 3 points. Okay, here we have more points. Here I have a few hundred points. So, and then you explain me how you get the margin of error. Well, later. Let's go back to this thing. Camera. Oh, no, share screen. I'm very happy. You are the first time that my students tell that they did this before. Every time I show the same thing and people say, oh, do you have to do replicas? And they kind of people, I don't know. Or maybe they don't and they don't want to speak. There is a point that we have to distinguish here that is kind of corresponding what Mirai showed. In biology, we distinguish what is called a technical replica from a biological replica. A technical replica is essentially doing the same experiment identically twice to see the only thing that can change is something about the technique. For example, here you drop the ball from the same starting position, 100 centimeters, and you may have some variability because of your speed of the chronometer or some variability that you didn't do exactly 100, something. There is some variability that you see in the horizontal line. But it's essentially the same experiment. Biological replica is equivalent here when you measure different starting points. So you will see variability, but that variability comes not only from your experiment, come from nature. For example, let's say you want to see, the typical example is you want to measure the size of cats. Let's say, what is the size of a cat? Well, first you have to capture one cat. You go to the street and you try to hold any cat that you find in the street. If you don't have a cat at home, but don't worry, Istanbul is full of cats. So first you will realize that measuring the cat is not so easy because cats move and they will fight you and they will move in general. So you have to measure the cat several times, okay? And you will have different numbers essentially because the cat is moving. That is what we call a technical replica. The same cat measured several times. The second point is that the technical replica gives you information about one organism. Then you have to capture more cats to have a general theory about cats. You have to go and capture many cats, and you set them free, you hold them for a while. But you have to measure several cats to get a general idea of cats in general. What is the size of a cat? Or if you want, the weight of the cat and the metabolic rate of the cat. No? If you want to replicate the paper that we saw in the morning, you have to measure the weight of the cat for several cats. Okay? That is an important distinction that is important when you plan your experiment. You need to do replicas, but you need to understand the difference between technical replicas and biological replicas. They are handled different the statistic is different. You have different hypotheses. So technical replicas, well, you read this, are a precise measurement about a single individual. When you focus in a single individual, a single cat, a single person, that is what we do medicine. You measure one person, biology, a difference of medicine, you care about all humans or all mammals or all cells. When you say that the carbon fixation mechanism works in all cells, not in this cell, but in all cells. In science, we care about everything, not a particular one. So if you measure the metabolic rate of one cat, you are not speaking about all cats. You need to measure several cats, because the question is not my cat, is all cats. And the question is not one particular, it's not this one, is all of them. Okay, that is the difference between science and medicine, but broadly speaking. Okay, but this touches two important points. One is that you need to plan your experiment, considering how many replicas you need to control the error, as you say. And the second, that the real question of your experiment is not about the particular individuals that you are measuring, but about all organisms in general. Maybe, I mean, maybe not all cell, but let's say all mouse, or all humans, or all plants, or all I don't know, rice. If you're working with plants, let's say, you will like to work not only with the plant that I have here in my home, but all plant of this species, or something like that. Okay, you want to get a general result that applies to all families or classes of objects, not just one particular. Okay. So, for example, Kleber law was not about whales or rats, was about animals. He says animals. And to be able to speak about animals, he needs to consider different animals. Okay. Questions? So, here I draw the, in the case of the free fall, we have a theoretical model that you should know, and I will get to it in a minute, but here I did a simulation. This is not real data, and you see how things should happen. And if you see it, looks very much like the plot, the picture that I showed you. This is the theoretical result, and this is the picture that I took. Again, this is the picture. And let's see, the theoretical result is this one, no? Okay, so just to give you an idea what's happening, in the simulated data, I start with this, where my initial point of simulation, the time, well, at time 0, I have a height of 2 meters and a speed of negative, because it's going down. Okay. And I get to here in like 0.4 seconds, 0.4 and 0.5. I travel the first meter between 2 meters and 1 meter in something like 0.42 seconds. That I think was the result that you got in your experiment, no? How much it takes 1 meter?
100 centimeters I did.
Yeah, 100 centimeters. How much time?
0.46.
Yeah. So in my prediction, it should be 0.42 or something like that here.
I get 42 too.
Okay.
40.
Yeah, but fine. It's margin in the margin of error. So if I use a semi-log scale, it doesn't look like a line. If I use a log-log, it also doesn't look. We need something else. In this case, if you know the model behind, we have a formula like this one. that has a constant a, then a constant multiplied by the time, and then a third constant. We have three constants this time, multiplied by time squared. Okay, let me say then the word that you didn't say. This is a parabola. Okay, it's a parabolic shape, and the parabolic shape is a second degree equation. So you need time and you need time squared. Okay. Fine. Yes, no? I mean, there's so many nice experiments that we can do with this. So this second degree formula is a particular case of a general that we call a polynomial. Polynomial essentially means that you have x squared, and until the power of n. Okay. The bigger n is the degree. So the second degree, you have number 2. Third degree, number 3. Exponent 3. The more exponent you have, the more the degree. Okay. So how can we do a polynomial thing, a polynomial model with linear thing? We need to do something like this. Something like the height, the vertical position depend on time squared. No, unfortunately, we cannot do directly this. If you try, something will happen, something that we will talk later, but you cannot do the model with time squared directly. You need an intermediate step that you need to create a column that here I am calling time squared. Okay? Times Q. That you see how we do. My data frame is called ball, and I add a column with mutate. I am adding a column times Q, that is time squared, and I think back to ball again. And now you see that I got this number. Okay, fine. And now we can do the regression like this. Here you have to be careful, because here is when the linear model is different from the plot. Until now, since we have one horizontal and one vertical, we can do plot and a linear model in the same way. Now, with the problem with this polynomial and following is that we will have several independent variables, still one dependent, one vertical, but we will have several, let's say, horizontal variables. Here we have time and time squared. Okay. So you can do, if you have two columns, you can have, and you will have different, now we have more coefficients. You have a bigger formula, you have more coefficients. So in general, you can have something that can have many components, and you can see how much is the factor for every component. So going back here 1 second. So we have A, B, and C. Okay. And these are the coefficients that we get here. The coefficient is 2, minus 2, and minus 4.9. So what are the meaning of this? Let me see, do I have here? Yeah, I put them here. Tell me, what is the meaning of this? Let me give you a quick thing. If time is 0, at the beginning of the experiment, time is 0, then you only have A. This is 0, and this is 0. Okay. If time is 0, this is all these are 0. So you only have A. Therefore, A is the height at the beginning, the initial position. Okay. That is A. In this case, I simulated starting from 2 meters. Okay. B, well, it's not very easy to see, but if you remember when I showed you the table, the initial velocity was minus 2. That is the initial. Like I'm starting like pushing down, okay? Which is not a very good idea, but we can assume that, well, there's 2 points. Like if you drop it, then the initial velocity is 0, which is a good idea. But if you don't, if you that is one of the errors, that you can kind of move it a little bit. You can give it a little push. Sometimes you do it without control. You can give it a little push. Well, then you are adding some initial velocity. And C, what is C? Well, you should know. What is C?
Maybe acceleration?
Exactly. It is, okay, say again exactly, just acceleration, but can you say again?
Acceleration.
Yeah, but to say may I say no? It's acceleration, which in fact is half the acceleration. If you remember the formula of the position depending on time is initial position plus speed times multiplied by time plus 1/2 acceleration times time square. Okay.
Okay.
So, and what is if -49 is half something? What is that something?
Gravity.
Yeah, I will say again.
Gravity.
So, gravity. So -4.9 is half of something. I multiply by 2, I get, no, that's not the correct minus. It's this minus. 9.8. So, okay, so, well, right now I'm just using simulated data, and in my simulation, I choose these values. In my simulation, when I make these synthetic values, I say my initial position will be 2, my initial speed will be -0.2, and the acceleration of gravity will be 9.8 negative. And then I want to calculate everything, okay? And when we do the model, we recover the initial parameter. So this is a toy problem in which I simulated everything. I know the result, and I showed that the linear model can recover the real values. Now let's do it for real. Let's go so the model even fits. So, well, I asked you this question already. So in our experiment, in the experiment that I did, I got this data. I will give you this data, but you have your own data, so we can even try. The problem that you have is in your data, you have only, you have 3 points, but several replica. Well, okay. We will do something with your data. We will do something. It is because we need to find a way to handle your replicas. So we can do something like we can collect everybody's data. I mean, if everybody did the same experiment, so we have a kind of biological replica, but everybody of you did different. And we can see, we can take an average of everybody, not only your data, no? That would be interesting. Yeah, maybe we can do some quiz. Something. Okay, next time. Library reader, and I read the table that I'm going to send you in a minute. But the point that we have here, I got this. I got the time in milliseconds as shown in the screen, in the video. This is my analysis of the video that I show you. I mean, if you want to replicate, you can look the video in YouTube and go picture by picture like I did, you know. I essentially went picture by picture and took the number here. And this was the position when it crossed the line 10. And then I had, in this case, I had two replicas that I call A and B. Like the replicas that you did. But to make it easy for today, I'm going to show, well, the result is this. I have the position. I started measuring from 10 to 20. And they are, in this case, going up because, remember, I put 10 in the upper position. It was a bad decision. I should have put the higher number up and then the other number down. So we need to change the sign here or do something like this. Position is upside down, initial time is not 0. And we have 2 replicas. So there is some timing up. The first timing up that I do here for today is that I am taking only the first replica. Later in another class, I want to use both replicas, but since you also have the data, I want to use your data. Okay, but for another class. Just one parenthesis. My initial idea was to show you this, and in the next class, finish this with the part with more replica. But I realized that we really need a way to make some graphics now. So in the next class, I want to make a parenthesis, study how to make nice plots, how to make plot of several data and something more nicer than what we see so far. And then in the last class, we finish this idea of replicas, the linear model with graphics and everything. Okay. So this will be the last time that we speak of linear models until we finish graphic. Okay.
Okay.
So here I have 9 values. And there is some adaptation that I need to do. Okay, let's see here. For example, so the timer started before dropping the ball. So I need to fix the time to make it, to kind of normalize the data. I want to change the data so when the ball crosses the first line, that will be my time 0. Okay. I should have the picture here, but then this will be our time reference. When the ball crosses the 10, that will be my time reference. I need to do that in order to make all replicas compatible. Okay. So the problem is that in that case, the ball is already moving, so initial speed is not 0. So I'm essentially, in my mind, A should be 0 and B should not be 0. Okay, I want to know what is B, because I dropped the ball a little higher, but I don't know how much higher. So there are 2 questions. I either, how can I say? I either control the initial speed or the initial position. And in this case, I cannot control the initial position. I cannot measure the initial position, so I have to measure the, I will, how can I say? I'm not explaining myself, but if I drop the ball here, but I don't know exactly when I am, where I am dropping it, I can drop from here or from here or from here. Then I have something that I cannot control. So what I can do is I know the time exactly when the object is crossing the initial line. That is the point that I'm fixing. So now I know the position, and on the other side, I don't know the speed. So that is a way to solve the problem. In a better experiment, I have to control the position very carefully and control the speed very carefully. I don't know how you did that. How you drop the, how did you do the experiment when you did your experiment? Can you explain me the experiment that you did very carefully? I mean, how you drop the ball? Was it a ball? What did you drop?
I drop a ball, like in this little. I drop it. I put a meter in front of my door, and I leave it. No, I drop it from the 1 meter, and I look at the time, and I note the times, And I make it.
Yeah, but you have to drop it and start the timer at the same time, and you have how you do it with 2 hands or.
You know, I remember now. I record it with video, and then I look at the video, the times.
And how you have the time in the video?
I start. The video give me the times. I look at the times, the seconds. I did
Okay, the time in the second. Yeah. I agree with that. But you know what I discovered doing this is that the video they say you is 30 frames per second or 25 frames per second, but it's not exactly like that. They have a margin of error. I mean, it's not. It's more like they probably have a high precision, but the real number is not the number that they say. For example, the European standard for cinema was taking 24 frames per second. Then TV, the European standard, including Turkey, is 25 frames per second. The American is 30 frames per second, or to be more precise, 29.97 frames per second. And then you have the high speed that should be like 120 frames per second, but sometimes 119 frames per second. So what I did is I put the watch, the timer in the screen, so I could compare the timer of the camera with the timer in the screen to have a second point. So you drop the ball and you have the initial time and then the initial position. Okay. Because there is another technique that people do with, they put a magnet, that you can control electrically. And you essentially, with the same timer, you drop the ball and start the counter at the same time because it's a magnetic thing that you can control. With the same button, you start the timer and you drop the ball. That gives you better precision. Anyway, let's finish the story. No, we have some time yet. So I make this, in my case, I make this fixing. Well, you know what is going, we can go fast here. You know what, essentially, I transform time from millisecond to second divided by 1000. So this is a new column called time in seconds. And then I correct the time. So the starting time is 0, as you say, which I'm doing this way. I'm taking the new value of time is the old value of time minus the minimum, which is the starting point. Okay. So here I got 0 and then 0.1 second and 0.4 second and so on. Okay. Now there is a point here that the values, and this is my main mistake, that I didn't measure the distance in centimeters. I kind of, because in the projection I try to, I can change the size and I say, okay, I will make it each one 10 centimeters. But in the class I forgot and I measured with a tape, but I didn't measure very carefully. So this is the main problem of error. And I think it was something like 19 centimeters, but to be honest, it should be done again. Then if it's true, then height is position that you see here, position, I counted 10, 20 or so, divided by 10 and multiplied by 0.19 meters. This is height in meters. So and measure from the top. So I start here. Well, this probably should be 0, no? Maybe position -1 here. Maybe I should fix it later. Okay, I'm going to check. Then this is what I got. And if you see, there is some points that are a little out here. Maybe this is a measurement error. And then I need to add the column time square. to do the fitting of the model. And these are my result here. This is the initial position. This is the time coefficient here is the initial speed in meter per second. And the time square is half of the acceleration. Okay. So this is my result, which is not very good, to be honest. But I don't know how it was compared to yours. .5. Oh, full. But I essentially think that with your 3 points that you got from your experiment, you can do something like this. You can put the 3 average, for example, and you with 3 points, you have enough to make a model like this. I have to fix height. Okay, this is not true right now. So let's stop here. Let's stop here. Okay. Again, the point of this is to insist again that the linear model is not only about making a prediction. The coefficient of the model are telling you something. In this case, our initial data is time and position. And the linear model is telling you what are the initial position, maybe that is easy. It's telling you what is the initial speed, and it's telling you what is the gravitational acceleration. And that is the interesting thing, that you can measure the gravitational acceleration with an experiment that can be done at home. Now, the margin of error is kind of big. So, and I think this is an experiment that, in my case, is not a very good experiment. So maybe we can try to do something better. Maybe. But the second point is this. You did with 3 points because, well, it is boring to do at home. But if you want to do it with more points, linear model give you a way to handle that data. Okay? You get more points, you can do more and more replicas and get something that is even nicer. Okay? Any question? So, and the other point is how we do these models, the polynomial models. We started last week with the linear model. In the morning, we saw exponential and a power law model that are with logarithm. The polynomial model doesn't need logarithm, as you see here. But what you need to do is to add a new column. This is the price that you pay. And if you have more degrees, you have to add more columns. If you have a third degree, you need to add time cube. If you need 4th degree, you can add more columns and have more degrees. Okay? And you can make a line that is softer. That is the price that you pay. You have to add more columns. Okay? And well, maybe the other time is that since you get more coefficient, you have to understand what is the meaning of that coefficient. What is the biological interpretation or physical interpretation? Fine, fine. Any question? That is my summary. No? Yes, no?